Hello everyone. So I'm Matheus, and I'm here to present the paper Reflection, Language Agents with Verbal Reinforcement Learning. So as the name suggests here, they try to do like some type of reinforcement learning, not really. It's more like verbal, so it's more like use and not like how do you train an agent with traditional reinforcement learning from what I got from the paper. But some ideas is like they propose a framework to how to kind of simulate this, and they have some advantages that they go into, like, oh, you don't need to fine tune a model and stuff like that, right? So I will explain the paper a bit more. So basically, here in the abstract, they start saying that large language models, the LLMs, they are really having a boom of usage, especially when trying to interact with external environments. You have games, you have things for programming, APIs, etc. But there is the challenge that sometimes it's very hard to leverage like some more complex tasks, right? So how you learn from your mistakes or your trial and error. So they say here like, oh, because traditional techniques like reinforcement learning require extensive training samples, but also model fine tuning. So here they propose the reflection. That's a framework that tries to reinforce these LLM agents by not updating the weights of the models, right? Which not be very feasible given the models that we have and stuff like that. But like they give what they call here like a linguistic feedback feedback. So like, oh, you do this, do that. So basically that's the idea, and I think it's very interesting, right? Because if you try to improve like your agent, if you in a given task, but you don't need to fine tune, right? So you can use the models that we currently use, right? So here, for instance, here they say that the reflection they tested in 3 different tasks, and it improved the state of the art, right? So here they say the coding, but they also have one for decision making and another more for reasoning. Okay. So basically, wait a minute. Basically, the model does not, like I said here, they say reinforcement learning, but they don't go into much detail on that. But just to give you a context for other people here, really layman terms, so not really totally correct, let's say. But reinforcement learning, you can kind of think that you have a place that's called the environment, right? And let's say that you are, I don't know, uh, let's say that you are a wolf. So, and then you have your nose. So you are the agent. And let's say that you have like, I don't know, have some ghosts like sheep, and you want, uh, in this environment, in this case, you want the wolf to eat the sheep, right? So it's kind of similar to a video game, right? So you have your agent, and let's say that your agent have a radius of what he can see, right? So he has to explore the environment, which can be like, let's say this square here, and let's say here. Oh, wait, here. Okay, so he export this and say like, oh, I saw this, and then like, oh, if I saw here, I can eat this and stuff like that. But then your environment can not only have good stuff for you, right? But also, let's say that you have like, oh my, I really pardon for the drawings, but I guess God, this is very awful. But let's say that you also have some traps in your environment, right? So it's a thing that maybe you want to avoid, right? So when the wolf, he, oh, sorry. So when the wolf, no, not this, is this one. Sorry. No. Well, anyway, so when the wolf goes here, he tries to avoid these traps, right? Because then he would be penalized. But how that works, right? So you have the environment, right? So let's put here. This square can be the environment. Oh, Wait a minute. Where's my screen? Okay. Environment like this. But then here you have you or the agent. And then what we want is like the agent interacts with the environment, and then you can try to set here what is called the rewards, right? And then you have also the state. The state of the environment can be like, for instance, the time elapsed, right? So for each frame of this pseudo animation can be a different state. Or for instance, like if you have a yeah, each action that you take kind of change the state of the environment, right? So basically, you can try to set some rewards. So like, oh, you have the wolf, and then let's say that each time he eats a sheep, he gets 1,000 reward points. So he learns that. And then for each time he goes to a bear trap, he loses 5,000 points. And if he eats all the sheep in the environment, let's say it's kind of like he got all the objectives, so he earned a further 10,000 points. I don't know. So what's the idea? The idea is that you use this reward here and to try to use this reward, and also I think that's the policy, to try to come up with the best sets of actions that maximize your reward and minimize any other, like losing, right? So for instance, you have the wolf here, and you want to try to get the sheeps while avoiding the bear traps, right? But at the start of the training, right, the agent will have some random weights. So basically, it will not know that the eating sheep is good and falling into a trap is bad. So at the start, he'll do some random actions, and then when he falls in the trap, but he'll receive a negative reward. And then when he eats chips, he'll receive a positive reward. So you kind of try to think that, oh, you have to avoid these bear traps and also have to eat this. So it's kind of like this. It's kind of like you think of a child, right? Like you as a child, like you put your hand on the fire hurts you, so that's kind of a negative reward, right? You say like, I won't do that again. But then you see like, I don't know, a cookie, and with cookie is good, so it's kind of positive reward. So you want more cookie, right? So it's kind of like this. So when people, I don't know if everyone is familiar with reinforcement learning, but very, very basically, that's how it works. So it's not all problems that can be approached as a reinforcement learning, right? Because you have this thing of the agent interacts with the environment, right? So if the agent doesn't interact with the environment, it's kind of how can you model this reinforcement learning problem, right? But anyway, basically that's how the idea of reinforcement learning. And I think the guys, the authors of this paper, they will go a bit into that, not too deep. Like I said, it's more like a verbal reinforcement learning, so it's more like cues instead of, you have a full model that updates the weights. But basically, I guess this is some explanation if you're not familiar with the term. Okay. So basically, here in the introduction, they talk a bit about some other recent works that try to leverage autonomous decision making for LLM. So we have the React one that they're going to use it later. So they say here, these LLMs, they can generate actions, but yeah, they rely on actions, but since they rely on massive models, wait a minute. Yeah. So since they can do this stuff, but since they rely on a lot of data, it's not feasible to do things like reinforcement learning with gradient descent, right? Which is basically what I said here, right? How a traditional model works, right? You have like the rewards, and then you apply some gradient descent to update the weights of the model that defines the actions of the agent to do that, right? It's not feasible in this context. So that's why they propose this alternative approach called the reflection that uses verbal reinforcements to help the agents learn from his previous failings. So basically here they say that, the agent, the reflection, it converts kind of like a feedback, like can be a binary or a scalar value into a textual feedback. So like instead of saying like, oh, you got it wrong or you got it right, it's more like, oh, you got this right, but this is a bit wrong, something like that. So that can be used to the LLM. So like they say here, like what they call the self-reflection, right? The self-reflect feedback acts as a semantic gradient descent, right? So instead of saying like, oh, the gradient, you should go in this direction to predict the weights or that direction, it's more like, oh, you should do this. It's more like a cue, right? So it's more interpretable, but also you can use the LLMs to do that, right? Here they say that, oh, it's a key to how humans iteratively learn to accomplish tasks, which, okay, I guess it's more interpretable than a gradient. I would agree with that. So here they say that it's challenging, right, to generate this useful reflect feedback, because you need to understand if the model makes mistakes and where it made mistakes, right? For some problems it's easier, but for other problems that is not clear, right? Like, oh, it's a problem that's more like a creative writing, for instance. It's not clear, like if it's good or bad or something like that. You can have some guidelines, but it's not clear cut, right? Okay. So basically here they say here like some advantages that it has compared to the traditional reinforcement learning approaches. First is like it's lightweight, it doesn't require fine-tuning the LLM, which I think is really interesting, right? Because you can test a thing and you have the costs of using the model, but apart from that, you can maybe kind of plug and play, right? So okay. So here, second, they said that it allows for more nuanced feedback, like they said, right? So instead of just having a number, or you got it right or you got it wrong, you can try to use the self-reflection module to give a further explanation of how you can try to complete the task. So here they say, oh, it allows for more explicit and interpretable form of episodic memory, which I think is interesting, right? Because they also have a module that's called memory. So the agent knows his past set of actions or experiences, and that can be used, to get to the final result. Here it provides more explicit hints of our future actions, which I think is kind of similar to the other points. But again, they also had some points that of concern that I think one is pretty clear, is that you rely too much on the LLMs, right? Because I think it's some other works that we have read or discussed in paper club, is that like, oh, they use the LLM to generate the ideas, to evaluate the ideas, to do everything, right? So it's kind of you kind of depend on that thing alone, right? But also at the same time, the thing is very powerful, right? So it kind of makes sense, but still it's a point of failure. But then he said like, oh, however, ILM improve, we expect that this will get better over time, which I mean, the problem is still exists. It still maintains the same problem, right? It's just that the model is more powerful anyway. Okay, so here they perform they say here the experiments that they perform, right? So they perform here in decision-making tasks, reasoning tasks, and some programming tasks, right? Which I think if you think a bit, kind of the type of tasks that this type of framework will really can lead to an increase, right? So they chose the best set of problems to present the framework, right? So basically that's it, right? So they propose reflection, which is a new paradigm for verbal reinforcement. And they also here they explore this is what they call here the self-reflection in LLMs, and they also test some in a set of ablation tests. They introduce a new reinforcement learning environment, but I don't think that's very interesting. I think the main point of the paper is the reflection framework. And here they show that the reflection achieves or breaks state of the art on several tasks. Okay. So for related work here, they say about of some, they break down some of the tests. So for reasoning decision making, they present some works here, but they argue here that in this paper is they really they show that it can be used like this work uses self-reflection to try to really is one of the first works to try to leverage this concept to try to improve the results. And here also in self-reflection here, they first saw that some LLMs here, that some work recognize here that LLMs can have like some cognitive ability similar to humans, right? So you have this paper that call for the theory of mind. They have some discussion on that, but at the same time, this work, they also state again, this is the first to try to use self-reflection for a practical use for autonomous behavior of agents. And then they use the self-reflection to amplify the sparse feedback, right? So like instead of saying like, oh, you got it, like I said, you got it, you fail or you pass, you're like, oh, you fail because of this, or you pass maybe because of that, right? Okay, so basically is this. So here I'm going to explain a bit later how it works, the framework. But first of all, let's explain like the main components of reflection. So the reflection is composed like of three main parts, right? First is the actor, so M of A, that generates the text and actions. So basically is I guess is the traditional thing that when you think of using, you know, ChatGPT or stuff like that, right? That would be the actor, right? Oh, generate a text for me. It generates, it's kind of like the actor. But you also have the evaluator, the M of E, that it basically scores the outputs produced by the actor, right? So, oh, you pass, you fail, or stuff like that. And then you have the self-reflection that basically generates the verbal reinforcement cues to assist the actor, right? So while the evaluator say pass or fail, the self-reflection say, oh, you pass because of this, you fail because of that, right? So basically that works. Okay, so the actor is built on a LLM, on a large language model. And basically, you have like what's called here a policy, which to me, given this context of the paper, is much more like the prompt that was originally used for the task, right? So, oh, do this task in this way. So that could be kind of the policy. But then you try to use this and maybe some part of past memories or extra context on your prompt to try to generate some actions, right? Here they say here that you know, they use some other prompt techniques like chain of thought and React, and basically that, right? I think I'll go into more detail later. The evaluator basically is the component of reflection that have really, they say here, the crucial role in assessing the quality of the generated outputs. So basically take the input, generate the trajectory, right? So have like the action that he took given the environment, like the conditions of the actor. And then it computes a score that reflects like the performance in this task, right? If it's good or not. So here they say some stuff here that sometimes you can use the evaluator to use a exact match, right? If the problem is kind of simple, but some parts they say here that they use some predefined heuristics, right? So, and I think that that they are tailor-made for the problem, right? Because I think this is the big challenge of this, right? Because you have some problems that are kind of simple to compute, that if you got right or not. But there are the problems that it's really, really difficult, right? So how you do that, right? But I think it's interesting to think of this, like the evaluator of how can we evaluate also if the task that we want to LLM to do it's correct or not. Finally, they have the self-reflection that basically is another LLM that has they say the crucial role of generating the verbal reflections that provide the feedback to the actor, right? So basically here, like, oh, give a sparse reward signal, and then you have the memory, the persistent memory that have information of past trajectories. Basically, you use that to try to generate feedback that's more informative, right? I think I say this kind of a lot of times, right? So you have a feedback that's more informative than just like base or fail. So basically here, so for instance, in a multi-step decision-making task, if the agent receive a failure signal, so you can infer that this action A that he took led to some incorrect future actions. So using self-reflection, you can verbally state that instead of using this action that led to failure, you should have taken a different action that maybe would yield in a more favorable results, right? So you kind of say like, oh, don't do that, try to do this thing, and then in the future, in the next step, the agent, maybe you change his route, his choice of action, and maybe you lead to a better result, right? I think here another thing that's really important is the memory, right? So basically here they say that you try to store information for past actions of the agent, but also the self-reflections. So basically like what he did before and what was his own reflections of the actions that he did before, right? So basically, I think in this context, he adds to the context, right? What I mean context, the context window, right? And then they say on the future work that maybe you could try to think about using other like a vector store and stuff like that, because I guess that would be great, that would be really interesting. But for this instance, I think they just focus on adding to the context window of the agent. So basically, yeah, like I said, you get the ideas like, oh, what I did before, what are my self-reflection of my past actions. So they use this to try to leverage improved results. Okay, so finally the reflection process, right? Can you guys read? See, it's okay. Okay.
Yes.
So basically here, just to explain a bit, so I have the algorithm and how their schematics, right? Okay. So basically, the first you have a set of policies or maybe a task. And then you have a memory that maybe at the start is just your context, your basic context window that you provided. And then you have the actor, and then actor provides some action, right? And then you interact with the environment, and then you use this, you compute this action, you save on your memory, your short-term memory, right? Oh, I did X. But then you use the evaluator here that will compute your zero action here, zero action using the evaluator. And then you use this feedback to the self-reflection model, and then you generate this self-reflection, the first self-reflection, using, again, the self-reflection agent, right? And then you use the self-reflection, you add this to the experience, what they call here the experience, which basically is the memory of what my action here led to, right? So basically that, and then you feed that back into the actor, and then here like it basically is a loop, right? So here's this initial set of actions, right? So you set the memory is the self-reflection that you had. And while you run this, while like the evaluator is not passed, like so it's failing the task. So until you pass the task, you run this while loop until maybe at next trials, right? Because then maybe you give up, you can solve the task. But basically, you use your actor to generate a future action. You store what you did, right, in the trajectory. You use the evaluator module to try to compute that and see like, oh, if that makes sense or not. you use the self-reflection. If it fail or it pass as well, right? Because then you can say like, oh, good job, you did the task correctly, right? But basically like, oh, you did this, or you fail again, and then like, oh, you fail because of this, maybe that, and then you start in the experience, and then you run again until you exceed your max trials, or until uh, you pass the test, right? So basically that's it. So for instance, let's try here again. So let's say that you have a task that, I don't know, generate ways with 3 words. Oh, sorry. So, and let's say you have an actor, a LLM, but the LLM is not that good. So first it generates, I don't know, we are the oh, I'm really sorry. Okay, we are the champions. So okay, so you generate first we are the champions, but then you store this, store trajectory. So basically store that, oh, I said this in the previous step, but then you get to the evaluator that basically say fail, right? Because you have 3 words and 1, 2, is 4 words, right? It's a very basic problem. So, but then you feed this fail to the self-reflection module that basically instead of just feeding the fail part, you just say that, oh, see this? Oh, your sentence seems to be uh, 4 words. Try something short. Try something short. I don't know. So maybe you give this like, oh, you're using 4 words, but try something shorter with 3. Oh, like, sorry. With fewer words, right? Try something shorter with fewer words. Okay, so basically you feed that, and no, then I have to write here again. So you store the self-reflection, right? And then you have the actor again to try to compute some action, right? So basically that's the idea. I think it's everyone got the gist of it, because basically you have a task, you store this, you run the evaluator, who run the self-reflection, and then if it's not passed, right, if it fail, you prompt again, but you add to the context, right? So instead of the context window maybe just be generate phrases with 3 words, and then you say like, oh, in my previous step I said we are the champions, but I did fail on the task, and maybe my sentence should be shorter with fewer words. And then you prompt the LLM again to run the task, right? Of course, this is a very simple example, right? Because we can compute this. We don't need to really the evaluator, right? A LLM to compute that. But just to give an example of how that should work, right? How the 3 LLMs try to interact with each other, right? I guess it's a bit clear. If it's not, just raise your hand and I can try to explain a bit more. But okay. So continue here after we explain how it works, the main idea of reflection. We have the experiments, right? So like I said before, they try to run on 3 different types of tasks: decision making, reasoning, and code generation. So they use different sets of data sets, right? So they use this hotpot QA, Word, and then some others for programming. It's really not, it's really dark here, but most notably, Reflection improved performance over strong baselines by 22% in Word, 20% in hotpot QA, and 11% in human eval. It's the programming one. So basically, it really achieved state of the art in these 3 different tasks. So the first one is the sequential decision making, is the Word. that basically here affords a suite for text-based environments that challenge the agent to solve multi-step tasks in a variety of interactive environments based on text words. So basically, the off word here is something that, of course, the LLM will only use the textual part, but off word is kind of like this environment, and then you have these objects, and then you have a task, right? Oh, you have all the objects that you have, and then your task is put some vase in safe. So basically here you have this example here of what can you do, right? You get to the location, on the shelf, you get a vase, you pick the vase, and then you go to the safe, and then you open the safe, you put the safe on the vase on the safe, and then you won, right? So basically it's very similar to maybe a text-based adventure game, right? That you don't have the things to click, but you know the objects, so you know uh, how to interact with the objects and how to try maybe to try to solve the task, right? So here again, like I said, they have like several environments, and then you have different tasks like finding hidden objects or move the objects. Like here in the case, like the objective here was to put vase in safe, right? So basically that's one objective. Okay, so basically they use React as the action generator. Uh, because they show here that it was kind of good, but they also use reflection on top of that, right? So basically, React is a type of prompting technique that basically you can try to generate some actions, give some context, right? So here, for instance, here. So you generate some thoughts, and then you have some actions, and so like, oh, I need to search app remote, program design to interact with. So basically you have some actions. So these actions can kind of be like how to interact with different APIs, right? So search app remote could be like, oh, you search for Wikipedia or something like that. So that's your action. And then you get the idea, and then you generate a thought again using the extra context, right? So basically it's this, I reason and act, right? So you kind of try to search, or could be like I said, like how you query, Wikipedia, or you look for external API, but of course, in this case of the off word, could be like open safe, or I don't know, anything like a close window, right? Is an action, right? Of course, yeah, kind of like this. So basically the results, right? So React plus Reflection, they argue here that outperforms just React in most of the tasks. And I think here is interesting here is this first graph that you can kind of see that, or maybe I will increase the zoom here, but basically here you have the React only is on gray here, and the others one on blue and green. And basically you can kind of see that the more the trial that you do, it increases the results, but without reflection, without this self reflection mechanism and stuff like that, the results, and I think in the other ones also is kind of similar, is that it doesn't prove too much the more you try, right? So you kind of get it. Maybe if you try again, maybe you have some small increase, but the increase is not that big. While in the others, like the more you try it, the more you get closer to a success ratio. Uh, so yeah, so here in the analysis, they see here that there's a big problem in this off-word environment is that the agent thinks that it has a possession of an item, where in actuality it doesn't have, right? So by using self-reflection, it kind of you kind of get a bit of more protection in this case, right? So here, reflection eliminates almost all of these cases by using self-reflection to distill long failed trajectories into relevant experiences that can be used as self-reads in the future, right? So like, oh, because here, I early mistake in a long trajectory can easily be identified, and then basically that's it. One thing that I think it's also interesting here is, here's, I guess it's wrong, right? It's all for the fail rate, because here they have like the proportion of the environments, how much they tried, but also the failure, right? So here you have on gray, here you have the react only, but the mistake was hallucination or inefficient planning. And for the same in yellow and purple, for the react plus reflection, right? So you can kind of see here that the more the trial number, you can kind of see again that the hallucination, it's the largest amount of errors that they have. Like I said here, like you have the item, but actually don't have the item. You think you have the item. You can kind of see that again, it plateaus at around 20% of failure. While with reflection, you can kind of see the more you tried, you plateau eventually, but it's way down, right? So you get you are able to mitigate hallucination way more than just by just using the React, right? I think this is very interesting, because it really showed that if you using this for loop environment, and then you have the self-reflection, you're able to try to improve in some aspects that maybe you wouldn't improve otherwise, or maybe not improve, but get to the satisfactory result, right? Satisfactory answer, sorry. Okay, so for the second one, they use the hotpot QA, which basically is a Wikipedia-based data set with various questions and answers. Basically here, so have an example here. So have a paragraph, so have some context here, like, oh, Josie and the Pussycats, the film, and then you have another paragraph for the actress Rosario Dawson, and then you have a question like, oh, what was Rosario Dawson of Josie and the Pussycats film's debut? So basically here, you can kind of see here, like, oh, she made her debut film in 1995, drama Kids. So of course here they are highlighting here, so just for you to see. But basically it's that, right? So you have some context here, and then you try to answer what's given, the question given the given context. So basically here, in this case, they implement reflection plus chain of thought prompting. So you have like a question to answer, or you have a question and the context with the ground truth to answer. Just because I think of the limitations of chain of thought, because here is not a multi-step decision-making technique, so they use here to try to isolate the reasonable behavior over large sections of the provided text. So basically, what is chain of thought, right? I think maybe that would be very interesting for a future paper, but basically it's another technique of prompt engineering, let's say that basically here you have a standard prompt. Here's an example of few shot prompting, right? So you prompt the model with some examples, and then in the end you have your question that you want to be answered. So maybe you can provide some how you want it to be answered, right? So basically you have, oh, Roger has 5 tennis balls, he buy 2 more cans of tennis ball, each can has 3 balls, how many balls he have now? So in this first one, the standard prompt, you just give the answer, and then you have another question, and then the answer you can see is similar, in similar structure, right? The answer is 11, the answer is 27, which is wrong. But then chain of thought prompt, instead of just giving the answer, you provide, for instance, maybe the same question, but then you do a chain of thought, right? So, oh, you start with 5 balls, right? And then he buys 2 more cans. 2 cans of 3 tennis balls, each is 6 tennis balls. And 5 plus 6 is 11. Therefore, the answer is 11. And basically here you do the same question again. And then instead of just trying to answer the question exactly, the model will try to output the same idea. So I'll have 23 originally, they use 20 to make lunch, and then they bought 6 more apples, and then the answer is 9. So you got to the correct answer. And basically here, like you can try to add like, for instance, here, a few shot prompting, right? So you add like different questions, but then you have like basically the idea like, oh, adding these numbers, the answer is true, the answer is false, instead of just providing for the model to answer, right? Because if you provide this idea of how to break it down, your thought process, pseudo thought process, right? It was shown that the model will improve results, especially for these types of problems that will require some basic math, right? Yeah. And I think just to add, I think it's really interesting that, like, oh, if you think a bit like this chain of thought prompting really requires you to do some few short examples, right? So in this case here, like, oh, adding the numbers to an even number. Then like, oh, you add like some 4 or 5 examples for the model to try to output something similar. But then some researchers here, they have the zero shot chain of thought prompting, right? That instead of, like here, the same example, right? Oh, you try to break it down an example question. Basically, you just answer like, let's think step by step. And then by just prompting the model that, the model will do something that's very similar to chain of thought prompting. They'll try to break it down the problem into smaller problems and then try to get a text that goes step by step to build the answer, right? So I think that's kind of funny, right? If you think a bit, right? Instead of doing a lot of things, you just like, let's think step by step, and then you kind of get a correct answer. Of course, this type of problem is kind of simple, right? But at the same time, I think it's interesting. Okay, so basically here they use, like I said, you have this question and answer data set, and you have the chain of thought implementation. They use 6-shot prompting, and then for React, they also use React. They use 2-shot prompting, and blah blah blah. Yeah, here they also said that they use the exact match answer grading, which I think is okay, but also is that part that is kind of dependent on the evaluator, right? Because it's this problem maybe is easy, but for more complex problems that would not be feasible. Okay, again, the results, the reflection outperforms the baseline approaches. And then here, I think more interesting that, let me just increase here. But I think here, it's really, they just chose maybe a different, I guess you guys can see, but here on clear gray, I think it's the same issue that I highlighted in the previous one, that the trial numbers for the models that don't use reflection, like the more they try, they don't tend to lead to an improved result. But if you use reflection, the more you try in that inner loop in the reflection mechanism, you tend to get better results, right? Not better results, but maybe some problems that you had that the agent would struggle to answer properly, it is able to answer after some retries, right? So you can kind of break down some actions that are not that good, or maybe you can get some action that was not obvious, but it led to the completion of the task, right? Yeah, I think basically that's the main idea, I think, here. Okay, so last but not least, you have the programming part, which basically here they try to do some programming Python and Rust, and then they try to use here like, oh, we include experiment for used code generation, reflection, just to prove that it's language agnostic, which I think it's more related to the data that was used to train the large language model than to the framework itself, but because you're not inputting, syntax and stuff like that of the language in your on the prompting, right? But well, anyway, they use that. They use for Python and Rust. And here the idea is that they try to self-generate some unit test suites, right? So like how you evaluate a programming, right? I think maybe it's something that maybe for more complex functions it's a bit harder, but I think it makes sense, right? To generate some unit tests to try to evaluate the function and see if that function works or not. And here in the results, they say that, oh, reflection outperforms all baseline accuracies for almost all of them, apart from this MBPP in Python. But yeah, but then again, like the previous state of the art was just GPT-4, and it's not stated which type of prompting technique, if any, was used. But also they used GPT-4 to base the reflection, right? Yeah, but one thing that's interesting here is that they acknowledge that the self-reflection code generation uh, can write some, comprehensive tests, but there are some cases that the test suite is not that good. So it's possible that you have here like a problem, like a true positive, a false negative, etc. So like, oh, you have a code for a function, but it fails in the test suite. But actually, the code was good, the function was good, but actually your self-reflection was bad. So it's kind of like it failed that, but the function was good. And likewise, you have the other way, right? You have a function that maybe is not that good, that does not complete the requirements, but the test suite just say like, oh, actually it's good to go this function. So it's something that you also need to really pay attention, especially if you want to deploy this automatically, right? Just code conversion. I don't know. Okay, I think we can go here to the limitations part of the paper. So here they say, right, reflection is an optimization technique that uses natural language to do policy optimization. And policy optimization is a powerful approach to improve action choice through experience, but it may still succumb to non-optimal local minimal solutions. And of course, this is like is a policy, but it's really, it's not that deep, right? It's just some verbal cues for your large language model, right? So it's, I think, another limitations that is not, the policies are not that defined, and it was not discussed in this paper, maybe in future work, like different ways that you can try to use a policy to improve the self-reflection modules, to improve the results of the agent. Okay, so in this study, we limit memory to a sliding window with a maximum capacity, but here, like I said, they encourage the future work to extend the memory component of reflections for more advanced structures. So you have, like I said, a vector embedding database or a traditional SQL database, right? Because again, it's still bound to the context window of the LLM, right? And this is, I think, with some people that work with LLMs know it's kind of like a problem, right? You always get the limit of how you can put, how much information you can put on LLMs to solve a problem. Here again, they say that no, the large language models, they are increasing the usage for external environments, right? So like all API usage, the internet and stuff like that. So here they argue that their work has the potential to empower and reinforce these agents to provide a greater level of quality of automation, but also amplifies the risks for misuse, right? I think also another very prevalent thing that appears on papers and research recently, right? Oh, AI for good. Oh, you can't. We are closing our model, like OpenAI would say, right? We are closing our model because AI is getting very dangerous, and we are the saints that will protect humanity, right? But anyway, but okay, but on the other end, reinforcement learning has suffered from its black box policy optimization setup, in which interpretability and alignment have been challenging. So their proposed verbal reinforcement learning might address some of the issues and turn autonomous agents more interpretable and diagnosable, I think. And I think that makes sense, right? Maybe it's not that strict, right? That you get to the optimal solution using this type of framework. But you can look at the prompt in the framework and kind of see like how the self-reflection module is trying to change the answer, right? In which direction, right? Even though it's not a direction, but like how he wants to update the agent output to get a better result. So, okay, so in the end here, they conclude that they present reflection, an approach that leverages verbal reinforcement to teach agents to learn from past mistakes, and that they empirically show that reflection agents significantly outperform currently widely used decision-making approaches by using this mechanism of self-reflection. And then in future work, reflection could be used to employ more advanced techniques that have been throughoutly studied in traditional reinforcement learning settings. So basically, you can try maybe to really apply some policy or some type of model that's more similar to really traditional reinforcement learning in this case, right? Because in this case, I think it's much more like a similar way, right, to apply reinforcement learning. But yeah, I think that's it, guys. Thanks for the time. But any questions?
I just wanted to comment something really fast. Uh, I remember a colleague that I had that said that there wasn't the teacher role in machine learning. It was a few years ago, and I think this paper kind of implements the teacher personality, trying to guide a student to the correct answer. But I still don't see how the teacher is like inputting knowledge inside the student uh, head. I don't know. And another thing is that the teacher could have their own biases. So it's also a problem, as you comment throughout your explanation, which was a very good explanation, by the way, Matheus. So
Thanks.
thank you. Yeah.
No, but yeah, I think it's really, yeah, I kind of agree with that, right? To kind of have some biases of the large language model, right? But I think one thing that maybe I don't know, I not that doesn't have a lot of experience with that, but I think that I kind of, when my test was able to kind of see is that large the LLMs, when you try to use, they are better at evaluating like the output than to solve the task, right? So maybe I think this breakdown of things can help, right? Even though it's not like, it's not that the evaluator or the self-reflection, they are more complex than the actor, right? Is right? It's more like they are, like they see the output, they just see the output, so they're like, oh, is this correct or not? And then the guy is on the outside and say like, yeah or no, right? So I think basically, to me, that's what I got, that maybe that I got right from
Yeah.
the work.
Yeah.
But yeah, I think it's interesting to think about like a teacher, right? But in which case that would be interesting, right? Because maybe what about the different model sizes, right? So maybe we could use a more complex model to evaluate the things, and then we use a more cheaper model, like a 7 billion parameter, do the action, and then use another more complex to evaluate. Would that make sense? Would that improve results? I think, because that's kind of interesting, right? Because to me, I don't remember seeing like what I said, that all large language models are better at evaluating than to do the action itself. But that's what I got from the like they said, the empirical experience, right? But yeah, I don't know, that maybe that could be interesting as well.
Yeah.
Okay. Any other questions, guys?
I was just not a question, but this made me think of like this idea of having distinct personalities constantly negotiating the behavior, and it's kind of like the Freudian idea of the ego, superego, and need. Like they're constantly negotiating and betting each other to decide. Kind of then you have this aggregate creature with the results of the three different identities.
And it's very neuroscience as well, right? In terms of, oh, there's the side of, that there's this competition with, oh, there's the side of the brain that wants to do the long-term objective, like lose weight. And then there's a short-term who wants food. And then there's something that wants to run, and then there's the other thing that's thinking about something else, and you kind of integrate all of those to get like a complex thought pattern and a complex planning, right? So I really thought it was really interesting, especially the part about memory and reinforcing memory over the long term. That is actually very useful.
And it's so funny to see like this, because if you think about neural networks coming from the knowledge that we have of neuroscience, somehow of inspired, and like now we are trying to take psychology, and now we're like not real frameworks like the ego and superego thing, and we are trying to compose on this too. It's funny to see those two sciences. I mean, no, science, it's a polemical term, but
Yeah, I think in a decade we'll
together.
have LLM psychologists.
Yeah, yeah, because that's if you think about it, that's way more about creating like not a real framework, like I mean framework in terms of algorithms, and more of a how do we like in a metaphysic way structure our thoughts.
Yeah,
And,
but
that's very interesting.
prompt engineering was called in the beginning like LLM psychologists, right?
Yeah, that's literally it, and that's very interesting. Yeah, I still think that this was going to be my comment. Like I still think that I'm biased towards thinking, yeah, but we are not incorporating this knowledge into the model itself, because that's how we've been doing machine learning for all those years. Maybe that's a bias. I don't know yet. But it would be interesting to see this being incorporated into the algorithms themselves. But maybe that's not how our brain works. I don't know.
Yeah, I don't know. If
Really
you think about it, like this training part is very harsh. I mean, imagine having to retrain one of these models every week, right? With new information.
Yeah, that's a good point. Yeah, but I also think that's if you consider all the hype of GPT and stuff like that, it's not obvious which is going to be the most common used approach, right, to solve these more complex tasks using LLMs, right? It's a lot of things that they are testing and checking and testing and checking, and also discoveries, right? So yeah, I don't know which one's going to be like the most useful, but I really think it's worth think a bit about it and maybe test in some cases that we have these new paradigms, right? But yeah, I think it's funny, right? LLM psychology, because it's kind of like they look humans, but at the other times they are really fail as humans if you think a bit. But yeah, it's how you deal with that, right? It's kind of like
Yeah, and knowledge is also kind of a social thing, like pass one to the other, and we build it collectively. So I think making the models interact makes sense if we make them behave accordingly.
Yeah, I think, basically based on what Gabriel said, it makes sense if we think about since LLMs hold so much knowledge, they might function better as like a society than individual people, right?
And we would also, like, if you think about a human under those circumstances, even if it is the same human in all of those roles, like we would perform better too. We would. It's very interesting.
A cool paper.
yeah. Okay, guys. Anything else?